Welcome to Study Smart Academy.
Today in this video, we will learn Class 10th Chemistry, Chapter 1, Chemical Reactions and Equations.
We are so glad you're here with us today. Students, we are going to figure out what a rusting iron gate and a stale, gross bag of potato chips actually have in common.
Right, because they definitely do.
They really do. And hint, it is the invisible math happening in the air right around them. So our mission today is to decode that math.
Exact.
We're going to learn exactly how to spot if a chemical reaction has happened, how to write and, balance the equations that describe them, and finally, how these universal rules apply to the real-world things you see every single day.
We're going to take this very slowly, students, and very clearly, step by step. But before we get into the heavy chemistry, let's establish the absolute basics. We need to understand the difference between a physical change and a chemical change.
Right, let's unpack this for a second. A physical change is a change where no new substances are formed. It is just the exact same stuff, maybe looking a little different. And crucially, these changes are reversible.
Reversible, yes. Make sure to write that down.
Right. We are talking about changes in the physical state, the size or the shape of a substance.
Think about it this way. Number one, melting of ice. If you look at an ice cube melting under a magnifying glass, the H2O molecules inside the solid ice are exactly the same H2O molecules in the puddle of liquid water.
Yeah.
The structure changed, sure, but the substance didn't. No new substance is formed.
And because it's reversible, number 2 is the freezing of water, which is just the reverse of that.
Exactly.
Number 3 is the boiling of water, turning it to steam. Number 4 is the condensation of that steam, where the gas cools and, turns back into a liquid.
Number 5 is making a solution, like dissolving sugar in a glass of water. You can evaporate the water and get the solid sugar right back.
Good point.
And finally, number 6, the glowing of an electric bulb. When you flip the switch on, it glows. When you turn it off, the filament inside is completely unchanged.
But a chemical change is a completely different story. In a chemical change, brand new substances are formed, and these changes are irreversible.
You cannot easily go back to what you started with.
No, you can't. The basic building blocks have rearranged themselves entirely.
So let's look at 4 classic examples of chemical changes.
Yeah.
Number 1, the burning of carbon. When carbon reacts with oxygen in the air, it produces ash and carbon dioxide gas.
Right.
The equation is literally carbon plus oxygen yields ash and CO2. You can't turn that smoke and ash back into a solid lump of coal.
Exactly. Number 2 is the rusting of iron. That strong, shiny metal turns into a weak, crumbly red rust.
Sadly, yes.
Number 3 is the formation of curd from milk. Once that milk sours and turns into curd, no amount of stirring is going to turn it back into fresh milk.
Oh, definitely not.
And number 4, the cooking of food. I mean, a raw egg is fundamentally changed once you fry it.
Which brings us to the official definition of a chemical reaction.
Oh.
Students, please write this down carefully. A chemical reaction is the process in which a substance undergoes change to produce a new substance with entirely new properties.
So to really visualize this, let's walk through a classic classroom activity. Imagine you take a 2-centimeter long magnesium ribbon.
Okay.
But step 1, before we do anything, we must clean it by rubbing it with sandpaper. Now wait, why do we do that? Why not just burn it straight away?
That is a crucial step, actually. Imagine a piece of metal sitting out in the air. Over time, it gets a dull skin on it. We rub it with sandpaper to remove that coating of impurity, which is usually a magnesium oxide layer that is formed on its surface.
Ah, I see.
Yeah. By scrubbing it off, we expose the pure reactive magnesium underneath.
Okay, so step 2. Now we burn that pure magnesium using a pair of tongs over a flame. If you were watching this in a lab, the observation here is just stunning.
It really is beautiful.
The magnesium ribbon burns with a dazzling, incredibly bright white flame, and as it burns, it changes into a powdery white substance.
And step 3 is identifying that powder. That white powder is called magnesium oxide. It is a brand new substance formed due to the reaction of the pure magnesium with the oxygen present in the air.
Let's write down the reaction equation for this on the board. We write 2Mg plus O2, then an arrow pointing to the right, followed by 2MgO.
Let me read that step by step for your notes. 2 atoms of solid magnesium plus 1 molecule of oxygen gas yields 2 molecules of magnesium oxide.
Perfect. So now that we know what a reaction is, how do they actually work?
Underneath it all, a chemical reaction involves the breaking of old bonds, which exist between the atoms of the reactants, and then the formation of brand new bonds to create the products.
If you want to play detective and spot one of these reactions, let's look at a very detailed example. Imagine a glass beaker on our desk. Inside, we drop some solid zinc granules, and then we pour in some dilute sulfuric acid.
The chemical equation for this setup is Zn solid plus dilute H2SO4, then an arrow pointing right to yield ZnSO4 aqueous plus H2 gas.
Let's break down the clues from that beaker. First, we would see the color of the zinc change from a blue-gray to white as it becomes zinc sulfate.
Right.
Second, we see bubbles. The reaction results in the evolution of a gas, specifically hydrogen gas, floating up.
Very noticeable.
Third, the zinc actually reacted with the acid to form a salt. So the actual chemical composition of our starting materials completely changed.
This gives us our detective's checklist. In your notes, students, create a summary box titled The 4 Main Indications. If you want to know if a chemical reaction has taken place, look for these 4 signs.
Okay, ready?
Roman numeral 1, evolution of a gas, like our bubbles. Roman numeral 2, change in state, like a solid turning into a liquid. Roman numeral 3, change in color. And Roman numeral 4, change in temperature, meaning the beaker physically gets hot or cold.
So how do we write all this down efficiently without writing paragraphs every time? We express it in the form of a chemical equation. Let's say hypothetical components A and B react to form C and D. The symbolic representation uses their formulas. A plus B, then an arrow pointing to the right, followed by C plus D.
Let's define the geography of this equation. First, the substances which combine or react are known as reactants. They are always written on the left-hand side, the LHS of the equation.
Got it.
We put a plus sign between them, which simply translates to the words reacts with.
Second, the new substances produced are known as products. The products are always written on the right-hand side, the RHS. Again, we use a plus sign if there are more than one, which translates to also forms.
Third, the reactants and products are separated by an arrowhead. The arrow always points from the reactants to the products, indicating the direction the reaction is flowing. You can read the arrow as the words to give or to yield.
To make these equations truly useful, we denote the physical states of the substances using tiny letters and brackets. Write these symbols down, class.
Very important.
A small s stands for solid. A small l is for liquid. A small g is for gas. The letters Q stand for an aqueous solution, which simply means the substance is dissolved in water.
We also use directional arrows. An upward pointing arrow next to a product means a gas is produced and evolving into the air.
Like it's flying away.
Exactly.
Yeah.
A downward pointing arrow means a precipitate is formed. A precipitate is just a solid that magically drops out of a liquid solution and falls to the bottom of the beaker.
If we look back at our zinc and sulfuric acid equation, we can see these rules in action. It was Zn with an S for solid, plus dilute H2SO4, then the horizontal yield arrow.
Right.
On the product side, we have ZnSO4 with an AQ for aqueous, because the salt is dissolved in the liquid, plus H2 with a G for gas. We could also draw an upward pointing arrow right next to that hydrogen because it's bubbling away.
But sometimes reactions need a little push to get started. They won't just happen on their own. We call these reaction conditions, and things like specific temperatures, mechanical pressure, catalysts, or sunlight are written directly above or below the yield arrow in the middle of the equation.
It's like writing the recipe instructions right on the arrow. For example, to manufacture liquid methanol, the equation is CO gas plus 2H2 gas. But if you just mix those gases in a jar, nothing happens.
Nothing at all.
They need extreme mechanical pressure. So right above the arrow, we write 340 atm, which stands for 340 atmospheres of pressure. With that condition met, the arrow yields CH3OH liquid, which is methanol.
Another beautiful everyday example is photosynthesis. The equation is 6 molecules of CO2 aqueous plus 6 molecules of H2O. Above the arrow, we write the required condition, the word sunlight. Without the energy from biological sunlight, the reaction fails. But with it, the arrow yields glucose, which is C6H12O6 aqueous plus 6 molecules of O2 aqueous.
Now, students, let's talk about the balancing act. A balanced chemical equation is an equation in which the number of atoms of each individual element are perfectly equal on both sides of the arrow.
Let's read 3 quick examples of perfectly balanced equations. First, 2H2 plus O2 yields 2H2O. Second, N2 plus 3H2 yields 2NH3. Third, Zn plus 2 HCl yields ZnCl2 plus H2. In all of these, the atoms on the left match the atoms on the right perfectly.
But why do we care? I mean, why must a chemical equation be balanced in the first place?
Because of a fundamental rule of the universe, the law of conservation of mass. According to this law, matter can neither be created nor be destroyed in a chemical reaction.
Oh.
This means the total mass of all the reactants must be exactly equal to the total mass of all the products. You cannot magically lose atoms, and you can't magically create new building blocks out of thin air.
Exactly. It is just like balancing a physical scale. If you start with 10 iron atoms on the left side of the scale, you absolutely must have 10 iron atoms on the right side when the reaction is finished.
So let's learn how to do this ourselves using a technique called the hit and trial method. We will walk through this step by step. Our target is the skeleton equation of iron reacting with water.
When we write it.
Here is the unbalanced equation. Fe plus H2O yields Fe3O4 plus H2.
Step 1. Write down that skeleton equation and count the number of atoms of various elements on both sides. Let's look at the elements one by one. For iron, Fe, we have 1 atom on the reactant side, but 3 atoms on the product side.
Completely unbalanced.
For hydrogen, H, we have 2 on the left and 2 on the right. For oxygen, O, we have 1 on the left but 4 on the right. The scale is completely uneven.
Step 2. Here is the secret trick. Always start balancing with a compound which contains the maximum number of atoms. In this equation, that is the product Fe3O4.
Right.
Specifically, let's target the element oxygen within it. To balance the 4 oxygen atoms on the right side, we must multiply the water, the H2O, on the left side by 4. So the equation updates to Fe plus 4H2O yields Fe3O4 plus H2.
Okay. Step 3. Now we balance the remaining atoms. Let's fix the iron, Fe. We have 3 on the right, so we need 3 on the left-hand side. We simply multiply the single Fe by 3. Next, let's check the hydrogen. Because we multiplied the water by 4, we now have 4 times 2, which equals 8 hydrogen atoms on the left. To balance that, we multiply the H2 gas on the right-hand side by 4.
Makes sense.
The updated equation is now 3Fe plus 4H2O yields Fe3O4 plus 4H2.
Finally, step 4. The final check. We count the atoms on both sides one last time together. Iron is 3 on the left, 3 on the right.
Hydrogen is 8 on the left, 8 on the right.
Oxygen is 4 on the left, 4 on the right. The number of atoms on both sides of the equation are completely equal. Hence, the equation is officially balanced.
Take a deep breath, students. You just balanced a complex equation. Now that we know how to balance the scales, let's look at the actual choreography of how these atoms interact.
There are 4 main ways they dance together: combination, decomposition, displacement, and double displacement.
Let's start with type 1, combination reactions. These are reactions in which 2 or more substances combine together to form a single brand new product. The general format is A plus B yields C. They merge.
Let's look at how this plays out in reality. Number 1, magnesium and oxygen combine when heated to form magnesium oxide. 2 Mg plus O2, with a small triangle over the arrow meaning heat is applied, yields 2 MgO.
Number 2, hydrogen burns in oxygen to form water. 2H2 plus O2 yields 2H2O. Number 3, carbon, like coal, burns in air to form carbon dioxide. C plus O2 yields CO2.
Number 4 has a massive real-world application. Calcium oxide, which is commonly called quicklime, reacts with water to produce slaked lime, which is calcium hydroxide. The equation is CaO solid plus H2O liquid yields Ca open bracket OH close bracket 2 aqueous.
This specific reaction is used for whitewashing buildings. A solution of that slaked lime is painted onto walls. Over 2 to 3 days, the calcium hydroxide reacts slowly with the carbon dioxide gas naturally present in the air.
It's a slow process.
Yeah, and this combination forms a thin, beautiful, shining layer of calcium carbonate on the walls.
It is fascinating to note that the chemical formula for solid marble is also CaO, CO3. The full equation for this whitewashing process is Ca open bracket OH close bracket 2 aqueous plus CO2 gas yield CO3 solid plus H2O liquid.
Let's move to type 2, decomposition reaction. This is the exact opposite of combination. Those reactions in which a single compound splits up into 2 or more simpler substances are known as decomposition reactions. The format is AB yields A plus B.
Imagine a hammer smashing a rock into smaller pieces. But what is the hammer? Let's look at the thermal section, where the hammer is heat. Example 1, when ferrous sulfate is heated, it decomposes.
2FeSO4 solid heated yields Fe2O3 solid plus SO2 gas plus SO3 gas.
That CaO product is quicklime, which is heavily used worldwide in the manufacture of cement.
Oh, wow, really?
Yep, in example 3, heating lead nitrate. 2Pb, open bracket, NO3, close bracket, 2 solid heated, yields 2 PbO solid, plus 4 NO2 gas, plus O2 gas, plus O2 gas.
Next is the photolysis section, where the hammer is actually light. The photon of light delivers just enough energy to physically shatter the bonds. This was historically used in black and white photography.
Interesting.
Yeah. Example 4, silver chloride placed in sunlight decomposes into silver metal and chlorine gas. 2AgCl solid, with the word sunlight over the arrow, yields 2Ag solid plus Cl2 gas. Example 5, silver bromide in sunlight does the same thing. 2AgBr solid with sunlight yields 2Ag solid plus Br2 gas.
And finally, the electrolysis section, where electricity is the hammer breaking the bonds. Example 6. When a strong electric current is passed through molten sodium chloride, it violently decomposes to give pure sodium metal and chlorine gas. 2NaCl liquid with electricity over the arrow yields 2N a solid plus Cl2 gas.
That brings us to type 3, displacement reactions. These are reactions in which one element takes the place of another element in a chemical compound. The format is A plus BC yields AC plus B.
To understand this, think of a bully situation based on the reactivity rule. Metals like zinc and lead are more chemically reactive or stronger than copper.
Ah, I see.
Because they are more reactive, they can bully and displace copper right out of its compounds.
Let's see that in example 1. When an iron metal nail is placed in a blue copper sulfate solution, the stronger iron displaces the copper. The iron nail gets coated in brownish copper, and the blue color of the solution fades away entirely.
The equation is Fe solid plus CuSO, 4 aqueous yields. FeSO, 4 aqueous plus Cu solid.
Example 2 is zinc displacing copper. Zn solid plus CuSO, 4 aqueous yields. ZnSO, 4 aqueous plus Cu solid.
And example 3 is lead displacing copper. Pb solid plus CuCl, 2 aqueous yields. PbCl, 2 aqueous plus Cu solid. In all three cases, the weaker copper gets kicked out alone.
Now for type 4, double displacement reactions. These are reactions in which two compounds react by an exchange of ions to form two brand new compounds. The format is AB plus CD yields AD plus CB.
Think of this like two dancing couples on a dance floor. Suddenly, they completely switch partners.
Example 1. Sodium sulfate reacts with barium chloride to form barium sulfate and sodium chloride. The equation is Na2SO4 aqueous plus BaCl. 2 aqueous yields to NaCl aqueous plus BaSO4 solid.
Now, note that solid symbol. A white precipitate of BaSO4 is formed. The new couple actually drops right out of the liquid dance floor and falls to the bottom of the beaker as a solid powder.
Example 2. Sodium hydroxide and hydrogen chloride react to exchange ions. NaOH aqueous plus HCl aqueous yields NaCl aqueous plus H2O liquid.
Example 3. Potassium iodide added to lead nitrate. Pb, open bracket, NO3, close bracket, 2 aqueous plus 2 Ki aqueous yields PbI, 2 solid plus 2 KNO3 aqueous.
In this partner swap, a beautiful bright yellow precipitate of lead iodide is formed and drops out of the solution.
Now let's explore a very specific type of chemical behavior, oxidation and reduction reactions. Let's define them clearly. Oxidation is simply the addition of oxygen to a substance, or the removal of hydrogen from a substance.
You see this everywhere in the universe. It's essentially nature adding oxygen or stealing hydrogen. Here are 5 quick examples of oxidation. 1. Copper heated in air gets coated with black copper oxide. 2 Cu plus O. 2 heated yields 2 CuO.
2 Na plus O. 2 yields 2 NaO.
3. 2 Mg plus O. 2 yields 2 MgO. All 3 of those are clear additions of oxygen.
4. 2H2S plus O2 heated yields 2H2O plus 2S. Here, hydrogen is removed from the sulfur.
5. 4 HCl plus MnO2 yields MnCl2 plus 2H2O plus Cl2. Here, hydrogen is removed from the chlorine.
Reduction is the exact literal opposite. Reduction is the addition of hydrogen to a substance or the removal of oxygen from a substance.
Here are 5 examples of reduction playing out. 1. If hydrogen gas is passed over that heated black copper oxide, the coating turns brown again because the pure copper is restored. CuO plus H2 yields 2H plus H2O.
2H2 plus S yields H2S.
3. Cl2 plus H2S yields 2HCl plus S.
4. ZNO plus C yields Zn plus CO. Here, oxygen is actively removed from the zinc.
5. CuO plus H2 yields Cu plus H2O.
Now, what happens when oxidation and reduction occur at the exact same time in the same beaker? We call them redox reactions.
Yeah.
Red for reduction, ox for oxidation.
Clever.
In a redox reaction, one substance gives oxygen or removes hydrogen. This helpful substance is called the oxidizing agent. The other substance which gives hydrogen or removes oxygen is called the reducing agent.
Let's break down a detailed example of a redox reaction to see who is doing what. Look at the equation. CuO plus H2 yield Cu plus H2O. In this reaction, the CuO, the copper oxide, is losing its oxygen. It is undergoing reduction, so it acts as the oxidizing agent.
Meanwhile, the H2, the hydrogen, is gaining that oxygen to become water. It is undergoing oxidation, so it behaves as the reducing agent. They work together.
Some other rapid-fire examples of redox. ZNO plus C yields Zn plus CO. Here, the carbon is oxidized to CO, and the ZNO is reduced to pure Zn.
Another is MnO2 plus 4HCl yields MnCl2 plus 2H2O plus Cl2. In this one, the HCl is oxidized to Cl2, and the MnO2 is reduced to MnCl2.
By the way, here's a quick note from the study material to remember. The burning of magnesium we did earlier, that is an oxidation reaction. Why? Because the pure magnesium takes oxygen from the air to become magnesium oxide as the end product. 2Mg plus O2 yields 2MgO.
We are in the final stretch, students. Let's connect all this math to energy changes in everyday life. Reactions generally fall into two energy categories, exothermic and endothermic.
Let's start with exothermic. Exothermic reactions are those in which heat energy is evolved or released outward into the environment.
Examples include burning coal, C plus O2 yields CO2 plus heat, or burning methane gas, CH4 plus O2 yields CO2 plus 2H2O plus heat.
But here's a crucial point from the text that might blow your mind. Biological respiration is considered an exothermic reaction.
That's right. During respiration, the glucose from your food combines with oxygen in the cells of your body to form carbon dioxide and water, along with the release of energy. The equation is C6H12O6 plus 6O2 yields 6CO2 plus 6H2O plus energy.
Now, wait a minute. Respiration. I am breathing right now, and I definitely don't feel like I have a raging coal fire inside my chest.
And that is the miracle of biology. The energy isn't released all at once, as burning explosive heat like a methane fire.
Oh, thank goodness.
Right. The body is smart. It uses enzymes to ensure the energy is released very slowly in tiny controlled steps, just enough to safely power ourselves without melting us.
Fascinating. Now, endothermic reactions are the opposite. These are reactions in which heat energy is absorbed from the environment, making things feel cold or requiring a constant heat source to keep going.
For example, N2 plus O2, absorbing heat, yields 2NO. Another is C plus 2H2, with heat applied, yields CH4.
And earlier, we saw the thermal decomposition of calcium carbonate. CaCO3, requiring heat on the arrow, yields CaO plus CO2.
Let's finish today's lecture by observing the slow, everyday effects of oxidation reactions around us. There are two incredibly common effects we battle all the time, the corrosion of metals and the rancidity of food.
Corrosion is the process by which strong metals are eaten up gradually by the action of air, moisture, or chemicals, such as an acid, on their surface. The metal gets oxidized to form metal oxides, which are weak and flaky. They peel off, exposing fresh metal underneath to be eaten away next.
The most famous, expensive example in the world is rusting, which is the specific corrosion of iron. It weakens bridges, cars, and gates, cutting their life short.
The chemical formula for this destruction is 4 Fe plus 3 O2 plus 2H2O yields 2 Fe2O3.XH2O.
That .XH2O at the end simply stands for a variable number of water molecules trapped in the crystal, and the whole thing is officially called hydrated iron 3 oxide, or rust.
We can prevent this costly rusting by painting the metal or by applying grease or oil to block the air and moisture. Another amazing industrial method is galvanization. This is the process of depositing a thin protective layer of a different metal like zinc, copper, nickel, or chromium right on the surface of iron objects. Think of those shiny silver bicycle wheel rims. They are galvanized to stop the vulnerable iron beneath from ever rusting.
The second everyday effect of oxidation is rancidity. This is the disgusting change in the odor and flavor of oily and fatty foods caused by oxidation. It spoils food materials prepared in fats and oils when they are kept out for a considerable time, making them taste terrible and unfit for eating.
Nobody likes opening a stale, foul-smelling bag of chips. Fortunately, food scientists have 5 prevention methods to fight rancidity. Number 1, adding chemical antioxidants directly to the food.
The two famous ones are BHA, which stands for butylated hydroxyanisole, and BHT, which stands for butylated hydroxytoluene. They sacrifice themselves to the oxygen so the food doesn't have to.
Number 2, packing foods in nitrogen gas. When manufacturers make potato chips, they intentionally fill the plastic bags with unreactive nitrogen gas instead of normal air. This creates a shield, preventing the chips from being oxidized.
Number 3, keeping food in a refrigerator. The low temperature simply slows down the oxidation of the fats and oils.
Number 4, storing food in airtight containers. If you lock out the fresh oxygen, you literally starve the oxidation reaction.
And finally, number 5, storing food away from light. In the dark absence of light, the energy required for the oxidation process is reduced, slowing it down.
And with that final concept, we have thoroughly covered every single detail, equation, and reaction of Chapter 1.
Class, you have done an incredible job following along with these complex concepts. Make sure you review your notes and practice balancing those skeleton equations.
Class is officially dismissed. Thank you so much for sticking through this video lecture with us at Study Smart Academy.
Before you close your books, I want to leave you with one final thought to ponder. Every single time you take a breath to power your body, or open a fresh bag of chips puffed with nitrogen, or walk past a rusty iron gate in your neighborhood, you're witnessing the invisible, perfectly balanced mathematical equations of the universe happening right in front of your eyes. How many other invisible reactions have you walked past today?
Keep observing the world, students. Thank you.